In this introductory video, we are going to look at the properties of logarithms. The properties of logarithms allow us to simplify or expand expressions and equations that might involve more than one logarithm. This would be kind of the logarithmic equivalent to factoring and combining like terms and the such. All right, so we're just going to get into them. Some of the properties are a little simpler, and some of them are a little more difficult. So we have a few general properties that should come pretty naturally if you've already had an introduction to logarithms and you pretty much understand your properties of exponents. So the first one says logarithm base b of 1 equals 0. The second is that the logarithm base b of b is equal to 1. Those should look fairly familiar if you have done any work with logarithms at all. The next, logarithm base b of b to the x equals x. And finally, b to the logarithm base b of x equals x. So we have these four general properties that we use. The first two, if we want to think about where they come from, what is their derivation? That's where do things come from. The first two come simply by using the definition of a logarithm. If you think about the first two and you took the logarithm statements and converted them to the equivalent exponential statement by using the definition of a logarithm, you would see where they come from pretty quickly. The second two, or that's not a great color there, let's choose a different color. The second two are built on the fact that what we're really doing is composing, so the composition of inverse functions. If you think about property 3 here, we have a logarithm base b. But the input into the logarithm base b is an exponential function base b. So we are composing inverse functions. And we know that when we compose inverse functions, they quote unquote undo each other, and we get the value that we started with back. Very similar, we have the same in property 4, that we have an exponential function with a base b, and its input is a logarithmic function base b. So I'm putting a logarithm into an exponential, so the logarithm and the exponential will undo each other, and I get the x, or the value that I started with, I get back. So keep those in mind as part of our simplification process. So for example here, just a few to work through. The first one says logarithm base 10 of 10. And truth be told, it's actually kind of silly to write logarithm base 10 of 10. I should probably just write the common logarithm of 10. And that is going to be equal to 1. You're really asking the question, what is the exponent needed on a base of 10 to give us a value of 10? And the answer is 1. Now, the second two are a little more interesting, and they get at properties 3 and 4. So I've got this natural logarithm here with an input that is the natural exponential function. So I've got a natural exponential function base e, being used as the input into a logarithm base b. Those two functions are inverses. Exponential function base b, logarithmic function base b. So I get an answer of x plus 3. They undo each other, and I get back what I started with. Similarly, in the third example, I have an exponential function with a base 10. I have a logarithmic function base 10. Those two functions are inverse. So when I put x plus 8 into the logarithmic function, get some answer. And I take that answer and I put it into the exponential function. the exponential function undoes the work of the logarithmic function, and I get the x plus 8 back that I had started with. Right? Right. So here's a few examples for you to try on your own. Maybe a good time for you to pause the video, try them on your own, unpause the video, and see how you did. Okay, I assume you're back from the pause. For the first example, the natural logarithm of 1, that is going to be 0. And we can just base that on the definition of a logarithm. We're asking the question, e to what power gives us a total value of 1? That's definition of a logarithm. The second is going to be x squared. And that answer is x squared because I started with a logarithm base 10, but its input was an exponential base 10. That says the common logarithm of 10 to the x squared. Whatever work the exponential function base 10 does, the logarithmic function base 10 undoes it. And the third example, the value is 2x plus 5. I have an exponential function base e whose input is a logarithmic function base e. Those are inverse functions that undo each other. All right, so those are what we might call the general properties. We have 3 specific properties that we would work with, and they have names very similar to the properties of exponents because of the relationship between the two. So the product property of logarithms. So we're going to have some variables in here. We need b, m, and n to be positive real numbers, so no negatives and not 0. And then p and x within this context are going to be any real numbers, positive, negative, big, small, anything flies there. All right? So the product property of logarithms says that if I have 2 logarithms of the same base that are being added together, so if I have logarithm base b of m added to logarithm base b of n, that can be simplified down to the logarithm base b of m times n. Now, just to remind everybody, any rule that has an equal sign can work in both directions. That means given the left side of this statement, I can convert it to the right side, but also given the right side, I can convert that to the left side. So we use this both to take separate logarithms and put them together, but sometimes we do use it to take a single logarithm and pull it apart. And this should look like the exponent property where we would say if I have like bases being multiplied, I would add the exponent. So we've got that idea of multiplying like bases with the adding the exponents, and that's where it relates there. So that's the product property of logarithms. The quotient property of logarithms follows fairly similarly. It says that if I have a logarithm base b of m, but I'm subtracting it with the logarithm base b of n, I will get the logarithm base b of m over n. So it says if I have 2 logarithms, same base, that's very important, same base, very important here, same base, very important. They're being subtracted. I can condense that down to a single logarithm where I'm taking the quotient of those 2 separate inputs. Once again, like the previous problem, I can take this from left to right or from right to left. Skip the slide there. All right, the power property, very similar, says if I have a logarithm base b of m raised to the p power, now that's the whole input like that, I can rewrite that as p multiplied by the logarithm base b of m. So this only has a single logarithm, just base b of some input. We don't have 2 separate logarithms. But it allows us a way to move that exponent from being an exponent on the input m to being a multiplication by the entire value of the logarithm. As usual, I can use this left to right or from right to left. Okay? Now, a couple of warnings here. These are things that people happen to do wrong. Some people try to take a single logarithm where we have m plus n and turn it into logarithm base b of m plus logarithm base b of n, but that is a big, big no-no. That is not true. It might be tempting, you might want to do it, but you can't. Similarly, a logarithm where I've got a subtraction in my inputs. It's very tempting to split that to two separate logarithms and subtract between the two. But that is a no-no as well. All right, so be careful with those temptations there. All right, so all we've done here is so far is introduce them. What I want to do now is I do want to prove these logarithms. I think we might hold off on that and make that in a subsequent video. So the follow-up video of this is going to start talking about why these rules are true, so you don't just necessarily have to take it on faith. All right, stay tuned for the next video, and I hope this just introduces the properties.